welcome to Physics 307. Our second gamma ray lab deals with Poisson distributions and excited state decay. So a Poisson distribution is a counting distribution. It's commonly used when you're counting up a small to a medium number of occurrences. So in the limit of large numbers of occurrences, it converges with the Gaussian distribution, which is a continuous distribution function. But the Poisson distribution is a discrete distribution function. And it has a form of So it has a form of mu to the x over x factorial times e to the minus mu, where mu is the average number of occurrences in a given interval, and x is the total number of events. So, and that has a shape that looks like this. So if I'm looking at probability on the y-axis, and on the x-axis I just have the number of events, right? And I want to look at a few different averages. So say I want to look at a mu of 1. So I have a system with 1 count per second from our gamma ray detector. So if I have a mu of 1, the distribution function is going to look something like this. It should be centered on there. If I have a mu of 4, then the function will look something like this. Sorry, this should be a little steeper. And now if I look at a mu of 10, I'll have something that looks a bit like this. Okay, the point that I'm not getting across in my picture is that as you go to progressively larger mu's, the width increases. But you'll notice that this is starting to look like a Gaussian. Okay? So you're going to do a few different exercises with these Poisson distributions because you have a pretty ideal method of exploring those by varying the count rate. With your gamma ray detector, you can look at these different regimes. So the important point with this is that for large values of x, this converges to a Gaussian distribution. For small numbers of x, you get a sharp skewed distribution that becomes Gaussian. So you'll be able to do a few different exercises with the Poisson distribution. So now let's talk about the actual physics that we're going to do in this lab, and that's excited state decay. So you'll remember from last time that we were looking at the decay of cesium to barium. And that we had an excited state barium nucleus that would decay down to the ground state. 95% of the time, the cesium decay would give us this excited state barium, which would decay to the ground state of barium, releasing the 662 keV gamma. So this is still our decay process that we're looking at. But now what we want to do is we want to remove the cesium from the equation. Okay? So we're going to use our special sources and flush the barium out of the system right after it's been generated. So we're only going to be looking at the barium. So we're not going to have the cesium there to generate more barium continuously. So we're just going to be looking at this process right here. Okay? Now, the number of gamma ray photons that we see corresponds directly to a number of decays. So for every gamma ray we see, an excited state barium is going to a ground state barium. So that means that the number of atoms we see So the change in the number of atoms that we see, which is related by this gamma ray photon. So the number of these corresponds to the change in n, okay? Per interval of time is equal to some constant times the number of atoms that we have available to us. Okay? So this is our radioactive decay equation. So, in order to get this into a more useful form, we can rewrite it as the integral of dn over n is equal to minus lambda times the integral of dt. And that's going to give us the natural log of n is equal to minus lambda t plus c, or exponentiating both sides, n is equal to e to the minus lambda t c, or sub n0 e to the minus lambda t. Okay. Now we want to rewrite this in even a little more useful form by getting rid of this constant lambda in terms of something that we know about the material. And when we're dealing with decay processes like this, we usually talk about the half-life of that material. So what we mean by that is we have n is equal to 1/2 n naught. Okay, so if we plug this into this relation above, then we get 1/2 is equal to e to the minus lambda t, or the negative natural log of 2 is equal to negative lambda t, which gives us t is equal to, lambda is equal to the natural log of 2 over t. And so this t isn't just a variable t, it's actually the half-life. Okay. So now we can rewrite our relation as the number of atoms present is equal to whatever we started with, times e to the minus, the natural log of 2 is about 1.44 t over our half-life. Okay? So, our experiment for this week is going to look at finding this half-life. And we can do that very, very accurately. In barium, this is about a little more than 2.5 minutes. Using our setup, we combine that to within 1%. So for this lab, you're going to use exactly the same experimental setup that you used in the previous weeks. You're going to use the sodium iodide simulation counter. You're going to start with your cesium source, but instead of just using that straight up, you're actually going to flush some saltwater solution through it to elute the barium out of it. And then you're going to look at this spectrum with the multi-channel analyzer in a scalar mode. So you're just going to be looking at what you'll do is you'll set the upper level discriminator and the lower level discriminator to isolate this 662 keV gamma. You're not going to look at the Compton events at all. So you're going to look at this photo peak as a function of time. And that's going to give you a beautiful decay curve. So you're going to look at counts per time as a function, well, counts as a function of time. And you'll see something like this. Okay? And then you'll be able to linearize this and get out a very nice value for the half-life. Should be within 1%. So that's the lab for this week. Please do let me know if you have any questions. Thanks.